Okay, my name's Paul Albertella and I work for Codethink. I've been contributing to ELISA since the start, and I'm the chair of the OSET working group. I'm going to talk about a couple of things today. I'm going to talk about the new approach to safety that the Codethink have been developing, which we've talked about at ELISA before, and which we've recently given a name, RAFIA. I'm going to tell you about the tool that we've certified, which is called the Deterministic Construction Service, or DCS. I want to talk about the approach that we took to certifying DCS and the part that RAFIA played in that. And then finally, I'll talk about the role that DCS can play in certifying a Linux-based OS. So the new approach to safety was a bit of a it didn't feel like a good term to keep describing this approach. So we've given it this name RAFIA, which stands for Risk Analysis, Fault Injection, and Automation. I'll just give you a quick summary of this. The principles are that we use STPA, that's System Theoretic Process Analysis, to analyze the risks for our software and to specify the safety requirements in the form of constraints. Now, a constraint is really just a specific requirement that we can verify. And in this case, it describes what the system or a specific component needs to satisfy in order to prevent or mitigate a risk. Some of these constraints will be satisfied by the software itself, but some will not. For the ones that are not, we need mitigations that can be implemented by the wider system or perhaps by an engineering process. We then derive tests and other verification measures from these constraints to verify that the software meets the requirements that we expect. And we also identify fault injection scenarios based on our STPA results. That's sets of conditions that can actually lead to hazards, to the risks that we're trying to avoid. And then we want to use these fault injection scenarios to validate both the tests that we developed to make sure that they actually catch a failure, and also the mitigations that we're expecting to be implemented by the wider system. And finally, we want to automate our construction, our verification process as part of a continuous integration workflow. And that's what DCS is focused on. So DCS is a design pattern for a construction process for building software components that are going to be part of a safety critical system. It's intended to be used as part of a controlled continuous integration process, which we described in some detail in the safety manual for the tool. And it also provides a way to verify that the required controls for this process are in place and effective. It also lets us validate the tooling that we're using as part of the construction process so that we can be confident that it isn't introducing additional risks. As you can see from the certificate here, it's been certified by Exeter using ISO 26262, but it's part using the tool qualification requirements of 26262. So it's qualified as a supporting tool for use in safety applications up to ASIL D. So this is part of a continuing journey for Codethink, and it builds on many years of work, not just with safety, but with construction and integration tooling. And although it's an important step forward on that journey, which takes us closer to being able to certify an OS based on Linux, it's not a complete solution. And because the certification here is a tool certification, it's not a system certification, it's not establishing a complete set of argumentation for ISO 26262, but it helps us to take one step closer. Now, DCS is, as I said, is a design pattern, and what's been actually certified is a reference implementation of that. But the purpose of this is the key, and that's really what the subject of the certification is. What we want to do is to be able to construct software from a controlled set of inputs. We want to do this in such a way that it's consistently reproducible. And we want to show that this property of reproducibility is independent of our specific implementation. So we want to be able to do it again, perhaps with a different instance of DCS, perhaps with a different tool or a different version of the tool. And we want to be able to automate all of this as part of a continuous integration workflow. And the continuous integration part is really important. I think underlying all of this is the principle that if we're going to use Linux and other open source software in safety, the only viable way to do that is to do it in such a way that we can consume updates to those open source software components and manage those updates in a way that enables us to still meet our safety goals. And with this in mind, we also want to use our continuous integration workflow to generate the evidence that we need to support the certification of our software and to show that we're continuing to meet those requirements. So this is based on a set of principles that are a key part of the RAFIA approach. I talked about RAFIA previously at ELISA, but I think we didn't really dwell on these principles in great detail. There's a lot of interest in the other ones. So the first principle here is that construction provides a foundation for many of the other engineering processes that we care about in safety. The most important of these are change and configuration management and verification and impact analysis. And all of these require us to have control over our construction process, or are required in order to have that control over the construction process. So if you can demonstrate that your construction process is controlled, you can have some confidence in these other processes as well. But in order to do that, you don't have to simply have control over the source code of your software and its dependencies. You also need control over the tools and the processes and the other inputs to that construction process. And if you can do that, though, you can then use some predictable characteristics of the process to support your verification and your impact analysis. And the property that we make use of is binary reproducibility, which is the ability to consistently produce this identical set of binary outputs from the construction process when you use the same inputs. So no matter how many times you run the process, you'll get the same results. You can also use the controlled process around this construction process to drive your safety processes. You're going to need to specify everything that's going into that process, and that's an important precondition for a lot of the other safety processes. It also allows you to manage tracing of requirements to tests and tests to results, the results of which are generated by your verification processes, which are all aligned around this continuous integration model. You can use it to manage different configurations for your deployed software. If you're deploying it to different hardware targets or constructing different versions for different products. And you can also use it to generate or to manage the evidence that you need to support your safety arguments, which is what you're going to be using to achieve your certification. So the goals that we had with the DCS were not only to implement a process that satisfies these principles using a set of open source tools. We also wanted to demonstrate that a CI-driven process can satisfy the general ISO 26262 criteria for development processes. We wanted to establish a viable strategy for using open source tools in safety. We wanted to demonstrate that RAFIA is a viable way to approach this formal safety process. And above all, we wanted to lay the foundations for using this approach to certify Linux-based operating systems. The challenges with this are ones that we've talked about at ELISA on a number of occasions, which are the open source projects, or they have some useful engineering practices, do not map to the reference processes that we see documented in the safety standards. It's also another question we needed to answer was how can we classify the tools that we want to use and work out how or whether they need to be qualified. ISO 26262 has a section on tool qualification that goes through the process of classifying them according to their impact on the outputs on the safety case and their ability to detect errors. So we need to be able to do this for the tools that we're using in order to achieve that certification. We also wanted to know how we could create and manage the documentation that we were going to need for certification, and how to work out what criteria that documentation actually needed to meet. And fundamentally, how can we manage future updates to the tools that we're using so that we don't have to recertify them every time they change? So the first part of this was really applying the RAFIA approach that we described as a sort of general approach with Linux in mind to tools. And the approach is really much the same. We used STPA to define our safety requirements, identifying what losses we needed to prevent with the tools, which in this case wasn't so much harm to people, but a loss that would lead to that harm to people if the software was deployed to a vehicle and cause such harm. But we wanted to look at the losses and hazards at a kind of a higher level for the overall CI process in order to understand what we needed to control and why, how that might lead to the kind of losses that we wanted to avoid. We're also using STPA to confirm what our system architecture is, so how the tools interact with each other and the roles and responsibilities of individual tools in that integration, how those tool interactions can lead to the hazards and the loss scenarios associated with those. So a loss scenario is a kind of a set of system conditions or failures that can actually cause one of these hazards to manifest. And ultimately we wanted to define some constraints, safety requirements that we need to be in place in order to avoid these hazards. So we then use this to implement tests and other verification measures and identify some fault injections so that we can then provoke the hazards and demonstrate that our tools either cope with them or that the system as a whole and the processes around it can mitigate those hazards when they do occur. And then, of course, we want to do all this as part of an automated process. We want to control the versions and revisions of the tools that we're using and all the other inputs to the build and test process, and use those tools in controlled execution environments. So this is a control structure that we developed for describing the overall continuous integration workflow. We use this to help to define the control process that we'd need around DCS in order to meet our goals. Many of the constraints that we identified came from our past experience with this sort of workflow and the sort of mechanisms that we put in place before. But we wanted to analyze them systematically to understand how they applied to our safety goals. Then within that structure, we focused in on the control structure for DCS itself. the controllers in this reflect the open source tools that we used in our reference implementation. So you can see that in brackets we're referencing GitLab and build stream. But the way we defined them was using roles and responsibilities for those controllers, so that the analysis could provide a design pattern rather than only describing how those specific tools worked. The idea here being that we could implement DCS using a different set of tools and use the results of this analysis and the defined constraints to verify that it's meeting the same goals. So the analysis is what kind of gives us our requirements and enables us to build our safety argument to say why we believe this particular integration of tools can achieve our goals and how that contributes to the safety goals of the tool as a whole. But we also need to actually record that analysis in a way that we can use it. And so to do that, we developed a syntax using YAML. YAMLs is useful because it's both machine readable and mostly human readable, which means that you can both use it as part of your automated processes and also read it easily when you're, for example, reviewing changes to it. And the value of doing this and managing the results as we would manage source code is that we can use exactly the same process to manage changes to it as we're using to manage the source code changes, and in fact the rest of the documentation that we're using. And because that's happening in a CI process, we can use CI tools to verify the changes to it and make sure that, for example, we're obeying all the syntax rules for YAML, and we can define a set of rules that represent a schema to dictate how the actual data should be structured and identify gaps in our analysis. So, for example, in STPA, every hazard needs to reference a loss, and every unsafe control action needs to reference a hazard. So we can use the tools to check that exists and confirm when our analysis is consistent and complete. And because YAML is only partly human readable, we can also use it to generate human readable reports, so that our safety assessors in particular didn't have to struggle through YAML, and they could just read a nicely presented PDF. Now, the tools that the format that we developed for this and the tools we use to verify it, we've actually made open source. You can see there's a URL linking to that, so you can go and have a look at those and play with them yourself. And there's some examples that match the STPA handbook examples, so you can follow through and see how we're recording those results using YAML. So we're also using the STPA to define our safety requirements, which is one of the reasons why we want to control the outputs very carefully, because they're a lot of the other processes flow from them. You can see some constraints documented here, and see that they're linking to hazards that we're trying to avoid, but it's also got linkage to tests. So by putting a reference to the test that's actually verifying that that constraint has been met, we're then able to go through and make sure that, firstly, that our constraints either have a test reference or a link to some other way of verifying them, and so we've got a complete coverage for our safety requirements, but also we can then check the results of those tests to make sure that they're actually passing, and then for any given change to our overall system that we're managing through our continuous integration process, we can say whether our safety goals are being met. And as part of that, we're also using some fault injections. So some of the tests are specifically simulating a condition that would lead to a hazard. So An example might be simulating an out-of-memory condition in one of your build processes and making sure that the build error is still detected and treated correctly by the system as a whole. And as I say, not all of the constraints can be implemented by the software itself. In some cases, it's about the processes that the end user needs to apply, and we documented those in the safety manual. An example being, you can have GitLab providing the access control and authentication mechanisms, but you actually need a process in place to prevent users from subverting that and finding ways around the problem, or around the controls. Now, to achieve this, achieve the goals of DCS, we need to have control over all of our inputs to the construction process and to the verification process, which means not just the target software and its dependencies, but also the actions that are required to construct and verify these, and the tools used to perform these actions. And in fact, the execution environments for these actions, because all of these things can have an impact on the end result. And since our goal and for our requirement is for the final output, the binary outputs, to be identical for a given construction process, we need to have very tight control over all these. And because we're talking about open source software, we also need to have a controlled ingress for those open source inputs. So we're not reading the source code directly from the internet. We're mirroring the upstream project repositories in resources that we control. So in our case, in Codethink's GitLab instance, and we have processes in place to protect the changes to that, so that if the upstream project dramatically rewrites history to remove something or change something, we can detect that and make sure that it doesn't inadvertently or cause an inadvertent change in the parts that we're using. And also we're consuming only specific revisions from that, so we're not consuming the latest master or the latest on a particular branch. We're identifying it by something that's going to be consistently referring to the same thing. So ideally a SHA reference or perhaps a tag. And changes to these revision references represent changes to the software that we're using. So when we make a change to those references, we actually need to verify that the software is still achieving its goals. And as I said, we also need to control the execution environments, both for where we're building the software, but also for where we're verifying the software. So you can do this with container images to provide a consistent environment for those jobs, but you want to control inputs for these and construct them just as you would for other software. So you can, for example, use a Docker compose script to construct your environment and store those scripts in a Git repository and control changes to those in the same way that you would control changes to your software. And update the images that you're actually using via the CI process, so that only the latest approved version on the master branch leads to the actual image that you're using. So in our reference implementation, we used GitLab's container registry to store the actual images, and we had individual repos to generate those images. And in order to achieve binary reproducibility, you actually need to put some additional controls in place for the build environment itself. When you're using a build orchestration tool, which is a tool that you use to actually gather the inputs that you need to perform a construction process, we were using build stream. You actually need to be able to control all of the factors that can input to that, which means the environment variables that are present in the file system, and also block access to external networks to avoid uncontrolled inputs from the internet. Now, this seems like quite a bit of a performance to achieve this goal, but so why are we doing this? Why do we want reproducibility, and how can we use it? Well, we can enforce it by controlling our inputs and controlling our build and controlling our environment. And simply being able to do that actually gives us a lot of advantages in a safety context. Being able to say that we have complete control over all these things allows us to make some claims right away about our software. Not claims about whether it's safe, but claims about how we can then be confident in the subsequent processes we do to show that it's safe. Now, the approach that we've taken is based on principles that have already been established and explored by the Reproducible Builds project, and used by other open source projects such as Debian. And so we were kind of able to build on a lot of previous work to do this. But it's also important that, having established you have a reproducible build, you need to make sure that you continue to check that it's reproducible, because the various changes to the inputs can affect that. So you need to be checking it regularly. But once you have established it, you can exploit it to tell you a number of things. If you have identical outputs with different inputs, then this tells you some things about the changes. If you've made a change to your target software, it means that that change has no impact on the software. So you can avoid unnecessary testing. You might think, well, why would I want to make a change which has no impact on my binaries? Well, the answer there is that if you're following a kind of continuous integration and update process, you want to be able to continue to merge changes, and some of those changes might not actually affect your software. They might be conditionally compiled, so they only apply to a different target architecture, in which case you don't expect them to have an impact, but you want to be able to move your move the version of the software forward so that you're actually able to take advantage of changes that build on that come later. If we get identical outputs with different tools or environment, in other words, if we've updated a tool to a new version or made a change to an environment, but we can still get the same output for our software build, then we can be confident in those updates. And if we don't get the same results, then that's starting to drive our impact analysis. If we can look at what's changed, then we can home in on which change it is that's affected our results, and we can use that as a basis for then looking at those changes and work out whether they have a safety impact. And we can do some other clever things. If you're using artifact cache, for example, which is a way that you can accelerate build processes by caching the results, the intermediate results of a build, then you can then check that your cached artifacts have not been corrupted. So if you've been building up these cached artifacts over a number of changes, and you've been using tests based on those, but you want to then make a release and make sure that your cache hasn't been inadvertently corrupted, then you can do a build from source, and you can compare that with the cache, a build using the cached artifacts, and if they're the same, then you've got some confidence in your cache. So we have this controlled process. We have a way of verifying that we have the controlled process in place, because we can consistently reproduce our builds. But we can then build on this process, this control process, to do some other things. And the most important one there is actually providing and managing the evidence that we want to use for certification. And to do this, again, we're extending what we're applying this process to cover not just the source code and the documentation associated with that, or the build configurations associated with that, but also the documentation and the requirements and the certification criteria that we want to use as part of our process. We can map the evidence that we have produced by this process to the certification criteria. in our case, we had a set of criteria that were based on the ISO 26262 and a tailored set of criteria that applied for tool qualification. We can, for each of those requirements, assert how it is satisfied, in other words, why we believe that we've satisfied it. And then we can link to the evidence of that, so that a document that describes it, a source code that implements it, or the test that verifies it, or the test results from the CI generated output that proves it. And because we're doing this in a coordinated process, we can manage all of this alongside the software. It means we have the same updates to the software, and the criteria and the evidence are all managed by the same process. We can, for example, make sure that where we've got references to supporting evidence in our assertions, we can make sure those links are actually valid and up to date. So if we've accidentally broken one by changing the document name, then we can pick that up and fix it. And we can also trace requirements to tests and to test results. And because our safety assessors aren't all confident at using GitLab, we can also generate some human readable reports for them as PDFs or even as spreadsheets. Now, just to be clear, this certification is about a tool qualification, so it's based on a tailored ISO 26262 process, which omits some of the requirements that just don't apply. So there's no relevance for the hardware design and some of the kind of product-specific requirements. But it does include all of the management processes that are required by the standard, such as functional safety management and change management. And we've also included some of the concept phase and software development criteria. So, for example, we did the hazard analysis using STPA, and we did do some software implementation. So most of this was using existing open source software, such as BuildStream and GitLab. But we did develop some scripts in Python to implement some of the features. So we needed to say how and why we could have confidence in that, and what measures we've got in place to provide that confidence. So although this was a tool qualification, a lot of the principles are equally applicable for a product certification. Just as we've used STPA to define the safety goals for our tool, we can use them to define them for the system, and derive the detailed safety requirements for those. And just as we managed all the inputs that we needed for certification in a coordinated process, you could apply the same principles there. The documentation as code principle is one that's useful there. It depends on what works for your particular organization, but managing documentation in the same way that you're managing the code means that you can have some confidence that they actually correlate with each other, and that's a really important thing to be able to show for safety. If you have a design but it bears no relationship to what you've actually implemented, then it's not very useful. But fundamentally, it also illustrates how you can iteratively refine a safety case alongside software development, which at first sight may seem to go against the principles, the kind of the V model principles that you see in standards like ISO 26262, but it doesn't really. I think that the V model isn't about a kind of a single flow waterfall. It's not you go down this side and then you go up the other side once. You do that iteratively. You repeat and you refine, and being able to manage both the kind of the safety requirements and the analysis that's going into that, and the software implementation and the verification that you do, all in a coordinated process, is fundamental to be able to implement that kind of model. And for anything involving open source, where you really do want to be able to consume changes to that open source software, it's essential to have this planned in. Now, the the role of DCS in future work is worth talking about. So as a tool, we can use it as a basis for qualifying and validating open source tool chains. What was qualified in this case was something providing the overall context for a construction. So it wasn't about proving that a given compiler was safe. It was about proving that the construction process around it and the statements we can make about the particular version of the compiler that we're using um, was what was covered by it. So we could then go ahead and say for a particular product where we're using this compiler and the compiler has this role, we can then start to make safety claims about it, and we can demonstrate that we have control over the version of the compiler we're using and what requirements we have of it. But also we can validate the tool upgrades once we've established that model by looking at what impact a particular change is going to have on previous builds. So if we have a build that we've done with one version of a compiler, we make a change to the compiler and nothing changes, then we can be fairly confident in the compiler. And also, the other important thing we gain from this is that it's an implementation of the control process that we've identified, which is very much came from the RAFIA approach anyway. It's not only an implementation of it, it also allows us to prove that the process is working. If we have control over all our inputs, then we will be able to achieve this binary reproducibility principle. And we can use that as part of the impact analysis, both for the tools that we're using and also for the software that we're constructing. And also where we need to actually support qualification of other tools, we can use DCS to actually identify where they have an impact and qualify what that impact is, and then use DCS to build it and confirm that our assessment of that impact is correct, and then use RAFIA to define and verify safety requirements from that. But as this is a ELISA and not a tools conference, in the end, what's this all for? Well, how do we apply this to building a Linux-based OS? So fundamentally, it's a design pattern for using and building open source inputs, and ultimately you're going to have to do something like this in order to consume open source in a safety project. I think you can apply a lot of the principles here with manual processes. I think our goal here was to automate that as much as possible and give you a way to verify that you have control over it. And obviously this is just as applicable to software that you're going to deploy to a safety system as it is to software that you're going to use in a tool. It's also a specification of the scope of a certification. Where I don't believe it's possible for us to certify Linux as a whole. I do believe it's possible for us to define a role for Linux in a system, specify how we're using it, what its responsibilities are, and then actually do a complete certification on that basis. And this is an illustration of how to do that. And also, we've specifically tried to come up with a model for managing and generating the evidence that you need to support that certification. And ultimately, it is kind of intended to demonstrate that the RAFIA approach is actually viable for a real safety use case. In this case, qualifying a tool, but as I said, the principles apply to products as well. And just to stress it again, I think this principle here of iterative refinement of safety analysis. Yes, we want to get to a certain point with our safety analysis that we are confident we have a coherent safety argument. But I don't think the safety analysis stops there. I think you want a process that enables you to continue to refine that safety analysis and the safety requirements as your product is developed, not just for during product development, but also for maintenance as well. If you're going to continue to take updates to your product over time, then that becomes really critical. That's the end of the presentation. I can see there's some questions in the chat. I'll have a look there. Philip asks if you use a tag-based approach constraint. I'm not quite sure I follow you, Philip. Can you elaborate a bit?
Sorry, I had to adjust my mic.
No problem.
What I was thinking about was to have the headers and something in this, if something in the system change. I know that we were discussing it in automotive work group, how to trace back if you suddenly get a new constraint or something, and then you need to ripple through all the parts of the analysis. And if you do a tag-based, then you somehow need to make your traceability through the items, right? This could be done by scripting or any commercial tools or so, or is it maybe due to the STPA analysis itself that it's self-contained, or it was something which I want to understand?
No, that's a good question. So I think this is fundamental to how you approach the definition of your safety requirements. If, as you say, if you're making a claim based on a particular set of source code, and your inferred design from that source code, then yeah, every time you make a change, you then need to kind of manually check those that those conditions still apply. The point of doing the STPA analysis and then deriving tests and other verification measures from it is that you've got that traceability. You're saying, what do I need to be true in order for this constraint to be met? And that's not necessarily how does this need to be implemented. It could be that the implementation changes completely, but the constraint you've identified is still met. And exactly how you do that for a given piece of functionality will vary, but it could be as simple as you're invoking this system call, and the end result is the same. I don't think it's going to be that simplistic very often, but the principle is that you break it down into constraints that need to be met. You demonstrate either through testing or through other means that the constraints are met, and then you don't have to look at the specifics of the implementation unless that is how you are verifying your constraint. So you might need to do that for some constraints. You might need to do static analysis, but if you can break it down in such a way that you can automate that process, then it becomes possible to do this at the sort of scale we're talking about. Did that answer your question?
Yes, thanks.
Okay. Ramesh asks, is there a plan to run a pilot project to verify the certification process? Do you mean for Linux, or do you mean for DCS? DCS, we've already done the project and got the certificate, but so I'm assuming you mean for Linux.
Yeah, it's for Linux.
I think that's the logical next step, is to actually pick a Linux-based use case and run through that process and certify it. I think going all the way with a product certification it would require really somebody who actually wants to create a product, and that's part of the challenge with standards like ISO 26262 is that they're for products ultimately. The advantage with doing a tool cert was that we had something concrete that at the end of it that we was useful to us and that we wanted to create. But yeah, so you'd actually want an OEM or a hardware manufacturer creating a sort of a platform to kind of go through this process in order to validate it. And I think yes, that would be the logical next step.
Okay, wonderful. So just to clarify, you do expect this to get into the OEM, say CI/CD systems using the tools, in addition to the Safe Linux certification, right? At system level, I think these tools are more useful, correct?
So the intention with this is illustrating how an OEM or a system integrator providing a kind of an input to an OEM could implement a process to consume Linux and to certify Linux in a safety role. And that's part of the reason why we did it as a design pattern. We used the open source tools that Codethink are most familiar with because we wanted to build on that understanding and also what we had to hand. But we deliberately did it as a design pattern to state what the requirements of those tools were, so that somebody could do it with another set of tools. So we used GitLab. You could use GitHub. We used BuildStream. You could, with a bit of additional work, you use another build orchestration tool. The principles were the key, and being able to sort of demonstrate it for a set of open source tools was the objective. But yes, implementing this for an OEM would be the way to do it.
Okay, thank you. Appreciate it.
Paul?
Yeah.
I have a question. Actually, since Ramesh asked about the pilot, but what we're doing right now for the Telltale, right, where we are trying to apply the STPA, isn't that like a sort of pilot also to try out this approach?
Exactly. So that's a pilot of the RAFIA approach as well. A part of it, yes. I think the reason for DCS was that for one thing, it's a kind of an area in which Codethink's got some particular expertise, so we wanted to go ahead and do it anyway. But also it's kind of to prove that the RAFIA approach has some validity in safety. We wanted to actually go all the way with an ISO 26262 certification, albeit for a kind of a tailored subset. But yes, we are piloting some of the other parts as part of the ELISA's work, yes. So Leonidas asks, which part of the overall presented approach is realized as open source? Would we be able to replicate the process outside Codethink? That's a good question. So all the inputs to it, so all the tools that we use are open source. You can look at the safety assessment report from Exeter and see what the principles are. We've released the STPA tools as open source. There are some parts of it that we haven't, but in principle, it's something that somebody could recreate using open source. And I think the reason for us sharing it here is that we're interested in the principles and the fact that you can apply those principles using open source software. And that's why we're engaging with ELISA to share those principles. So if you wanted to do an implementation of DCS and get it qualified by Exeter, it would be easier because they've already certified ours. But yeah, I think talking to Codethink about how we did it would probably be the shortcut to that. Okay. Ted asks, can you give some examples of fault injections that you do during the RAFIA process? I think I mentioned one of them during my talk. So the use case that we were looking at was construction. So we wanted to identify what things could go wrong as part of that construction process that would cause us to miss the fact that that something undesirable had happened, that to cause a change to creep through that we hadn't noticed. And one of those was if you have something like an out of memory condition that's happening in one of your build processes, does that actually get detected as an error, or does it get accidentally missed and registered as a pass when you should have been registered as a failure? Some of the other ones we looked at were more about some of the technical implementation details. So I think I talked about how we were using binary reproducibility to check our artifact cache. We actually did some fault injection in the artifact caching mechanism to demonstrate what would happen if we poisoned the cache, and would we detect that in the process, and then could we detect it with the binary compare at the end.